Welcome to this masterclass explainer on the rigorous design and mathematical derivation of analog PID and lead lag controllers using operational amplifiers, or op-amps as we usually call them. Prepared by Dr. Nima Madian, this session is going to operate at a true university level. We're going to meticulously dissect every single circuit, every transfer function, and every block diagram, step by step. So let's dive right into this masterclass and see how we transform these theoretical ideals into physical, industrial-grade realities. Here is our agenda for today. We'll start with op-amp architecture and laws, move into atomic control units, then the component mapping matrix, parallel PID controller assembly, the lead-lag compensator standard, and finally, our final operational mandate. Okay, Section 1, op-amp architecture and laws. Let's lay down our absolute ground rules. Right off the bat, you have to notice the sheer demand for exactness here. Check out the precision junction and the critical path laid out on this schematic. We're looking at the fundamental triangle of the op-amp, but what's really highlighted here is the absolute, non-negotiable need for zero offset calibration. You know, in control systems, a millimeter of theoretical error basically turns into a mile of industrial catastrophe. Maintaining stability means you have to strictly adhere to specification compliance. And we're talking about tolerances as tight as plus or minus 0.0001%. To actually maintain that crazy level of precision, Dr. Mahadian lays out these 9 immutable laws. And when I say immutable, I mean they are strictly non-negotiable. If you look at the grid, these laws dictate everything, from never interchanging your positive and negative terminals to never, ever removing your offset compensation resistors. You don't change the feedback path, and you definitely don't alter the grounding. In analog control, getting creative with your circuit topology usually just leads straight to runaway saturation. Discipline is literally your only safeguard here. So this brings us to a crucial point, and I honestly cannot overstate this enough. The absolute most critical rule for engineering integrity is that you must never attempt to redraw these circuits from memory. Think about it. Human memory is lossy and prone to error, but an op-amp circuit is exact. You have to copy these uploaded circuits precisely as they're presented, no exceptions. Here we see the baseline architecture, which is basically the bedrock for everything we're going to do next. Notice the strict polarity. The input goes right through resistor R straight into the inverting or negative terminal. If you reverse this, you flip the entire logic from stable feedback into complete runaway saturation. Also notice the absolute reference to ground, and crucially, look at that RM resistor on the non-inverting terminal. That RM neutralizes the inherent amplifier bias currents, which provides our offset elimination. Seriously, never remove it. Moving on to Section 2, Atomic Control Units. Let's break down the P, I, and D functions. Our very first atomic unit is proportional control. And this is where you see how beautifully simple analog math can actually be. Just take a look at the transfer function. The output voltage over the input voltage in the Laplace domain is just determined by the negative ratio of the feedback resistor, RF, to the input resistor, R. Now, because we're feeding this into the inverting terminal, our gain is inherently negative. If you need an overall positive gain in your setup, you just slap on an identical inverted stage with a gain of -1 right in series. Simple as that. But what happens when you actually need dynamic tuning out in the field in a real industrial environment? Well, check out the Mitsubishi P controller. By introducing a potentiometer, which you see represented by resistors RP and RP at the output stage, Mitsubishi engineers came up with a brilliant solution. It allowed for precise fractional gain tuning, where that coefficient A is less than 1. This basically lets operators tweak the gain on the fly without ever altering the primary feedback loop structure, which means no risking sudden instability. All right, let's step it up to two-dimensional control and see how this builds. When we add a capacitor, CF, to the feedback loop in series with RF, we instantly graduate from proportional to proportional integral, or PI control. The math to circuit mapping shows exactly how this works. The integral time TI is now a direct product of the feedback resistor and the feedback capacitor. Essentially, it accumulates past error over time, steadily pulling the whole system to a zero steady-state error. Conversely, take a look at the derivative controller. By just placing the capacitor C on the input stage, right parallel to the input resistor R, we change the mathematical behavior entirely. Now, our derivative time, TD, is the product of input resistor R and input capacitor C. So instead of accumulating past error like the PI setup, this circuit reacts to the rate of change. It's essentially predicting the future error before it even happens. Pretty cool, right? Okay, Section 3, Component Mapping Matrix. Let's visualize how all these controllers stack up. This is a fantastic summary. Here we see all three of our controllers right side by side. Panel 1 is proportional, just resistors reacting entirely to present error. Panel 2 is integral, capacitor in the feedback loop, reacting to past accumulated error. And panel 3 is derivative, capacitor on the input, reacting to the future rate of change error. This visual layout just makes those core variables, K, Ti, and Td, incredibly clear and intuitive. Now let's look at a really fascinating real-world application of this. Look closely at this architecture pulled from the NECA power plant. Now, reaching a perfect, pristine mathematical derivative in the real world is notoriously difficult because of high-frequency noise. So what did they do? They ingeniously generated a derivative by nesting an integral controller inside a negative feedback loop. Look at that loop structure. The input is being summed directly with the negative of the integral output. And the reason this NECA power plant workaround actually functions is all rooted in this specific mathematical approximation. If you run the exact math on it, the transfer function becomes 1 over 1 plus 1 over Ts, which then simplifies down to Ts over 1 plus Ts. Now, assuming the product of integral time and frequency S is much less than 1, that denominator basically just approaches 1, so the result roughly equals Ts, giving us a pure derivative function. It's honestly a brilliant industrial workaround. But we have to remember our rules. This component mapping warning table hits on exactly why you must never redraw these from memory. If you swap just a single component, literally just moving a capacitor from the feedback network over to the input network, you radically change the controller's math from a 1 over S integrator straight to an S differentiator. The difference between beautifully stabilizing a system and causing a catastrophic oscillation is literally just the placement of one single component. Let's move into Section 4, Parallel PID Controller Assembly, building out the full modular structure. So here it is. This exact schematic displays the master transfer function. We are practically achieving full PID control here by continuously summing the outputs of these parallel, proportional, integral, and derivative paths. Over on the left, we've got the derivative and proportional input networks feeding into that first op-amp. The second stage is handling our integral components, and then that final stage, that's simply an inverter, a sign changer, to make sure our overall master transfer function has the correct positive sign for standard applications. And of course, the exactness of our schematic directly dictates the math. By systematically expanding the numerator of our parallel circuit step by step, we pull out the R and C values. We rearrange those terms, and suddenly, boom, the standard form of a PID controller emerges, Kp plus Ki over S plus Kd times S. And if you look at the bottom, this explicitly defines our Kp, Ki, and Kd constants based entirely on our specific R1, C1, R2, and C2 values. It all just falls perfectly out of the math. All right, Section 5, lead lag compensator, standard. Time for some advanced standards. Now we have to face the realities of high-level control. Because a perfect derivative is so hard to achieve, we often use this, a phase lead network feeding directly into a phase lag network. This creates a nested parallel and series RC architecture. The system transfer function here is highly complex. It manipulates phase angles to stabilize really difficult, stubborn systems without accidentally amplifying all that high-frequency noise. And please read the strict warning box here. You must copy this uploaded circuit exactly as it is. Do not attempt to optimize or fix it. And finally, Section 6, our final operational mandate, the definitive implementation rules. We've covered some intense mathematical mapping today. But the big question we have to ask ourselves now is, how do we actually ensure these beautiful mathematical ideals survive the messy reality of real-world implementation? Because frankly, all of this rigorous theoretical knowledge is completely useless without the disciplined execution of an operational mandate. So here is your approved checklist for implementation. You must execute the exact schematics provided. You absolutely must protect your offset resistors, do not bypass RM, maintain absolute grounding integrity, never, ever alter those feedback loops, and the golden rule that dictates whether your control system survives or fails, never redraw from memory. As you take all this knowledge from the theoretical slide to the actual soldering iron, ask yourself one question. Are your designs going to be built on the fragility of memory, or are they anchored in engineering exactness? Keep learning, keep building precisely, and we'll see you in the next explainer.